In this video, we solve problem 4.7.12 from Nagle's Fundamentals of Differential Equations with Boundary Value Problems, 7th edition. We're asked to find a general solution to the given Cauchy Euler equation for t greater than 0, and we have this. Now, on the surface, you may think that this is not a Cauchy Euler equation, but I'd like you to notice that the t's in the denominator here. If we multiply this equation by t squared, then we'll have the form of the Cauchy Euler equation that students in my class are accustomed to. One of these t's will reduce, both of these t's will reduce, and we'll have a t squared times the second derivative plus 13t times the first derivative plus 35w. The power of t and the order of the derivative multiplying it match. So that's second power, second derivative, first power, first derivative, 0th power of t, there's no t's, and then 0th derivative. So this is a Cauchy Euler equation. It's just written in a slightly different form than we're accustomed to. And I think I'll change to prime notation. Notice that our dependent variable is w rather than y. And that's okay. We can always switch to w. Okay. Since it's Cauchy Euler, we're going to let the form of the solution w be t to the m, where m is a number to be determined by us. And since it's second order, we'll compute w prime and w double prime, and then we will substitute those into the differential equation. Because we know that if w is actually a solution, then if we plug all these into the equation, then we should get 0. And then we'll have an equation involving m. And if we can find the values of m that satisfy that equation, we will know the types of functions that will satisfy this equation. So that's the plan. So let's do it. The derivative of this by the power rule is that power times t to the 1 less power. Second derivative, bring the constant down, bring the power down, multiply by t to the 1 less power. Distribute the m. And then you want to substitute into the differential equation. So we've got t squared times w double prime plus 13t times w prime plus 35 times our w, which is t to the m. Set that equal to 0. Now, whenever you're multiplying powers of t, you add the exponents. It's like we've got m minus 2 copies over here, and then we've got 2 more. So how many t's are we multiplying together? Well, this many plus this many. So we've got t to the m minus 2 plus 2 copies of t. So that when we add the exponents, we get t to the m. And similarly over here, we've got a t to the first and t to the m minus 1. When we add those exponents, we have t to the m, and then we have a t to the m over there. So we have t to the m as a factor of all of these, and that's just because it was Cauchy Euler. The power of t and the order of the derivative matching it are the same. So if we start with t to the m, if we take the derivative n times, this is going to be t to the n minus m, or m minus n, however many times we took the derivative. Well, this will always compensate for that because this pattern holds where this power of t and the order of the derivative match. So every time you do this, you should be able to factor out a t to some power, and it'll be t to the m if it's written in this particular form. It would look a little different if we left the t's in the denominator. Okay, so now we say to ourselves, t to the m times what gives us this first expression? Well, we're just missing the m squared minus m. And t to the m times what gives me this expression? Well, I have the 13m. And t to the m times 35 gives us the last part. We're saying this times this equals 0, and t is strictly greater than 0, so this is never 0. So we have m squared plus this guy, which simplifies to 12m, plus 35 is equal to 0. And that is the characteristic equation for our Cauchy Euler differential equation. If we can find the values of m that satisfy this equation, then we know the form of the solution for this equation. The m values that satisfy this are the m values that cause t to the m to be a solution of this equation. So this is quadratic, so you could use the quadratic formula. I prefer to factor if I can. So I'm looking for 2 numbers. that give me a product of the last term there, that constant term, and a sum of the middle term. So two numbers that multiply to give me 35 that add to 12. 5 and 7 will work, so that'll be plus 5 and plus 7. So this times this equals 0. If this factor equals 0 or this factor equals 0, this factor equals 0 when m equals -5. Just set that equal to 0 and subtract 5 from both sides. If we set this equal to 0 and subtract 7 from both sides, we get another root of -7. So we've got distinct real roots. So each of those corresponds to a solution, and these are w's, not y's. I'll call it w sub 1 and w sub 2. The first solution is t to the m1. The second solution is t to the m2. And then the general solution is w equals c1 w1 plus c2 w2, which is c1 times t to the -5th plus c2 times t to the -7th on the interval from 0 to infinity. Again, we just find the general solution by taking the w's, multiplying them by constants, and adding them together when referring to a homogeneous equation. And since it's second order, we only have two terms in our general solution.